Okay, so as we are moving from basics toward now the I will cover today the solar photovoltaics concepts on the today's lecture. So from basics we are moving toward the solar photovoltaics, then we will move toward the solar thermal devices. Okay, so before starting from today's lecture, as we are going into deep into tech side, so may I know your backgrounds and means are you a working professional or student or undergrad or postgrad student? So you may please share about yourself one by one. Then we can start the session. So on this, anyone can take the lead. I'm seeing here a few names in my screen. Ankur Pal is here. Purvika is here. Sunil Kumar Pandey.
Yes,
Please,
sir.
yeah, please share.
Myself, yes, sir. Myself working professional in thermal power plant. I want to upgrade my skill in solar power plant.
Okay,
That's why I joined that process.
okay. So it's a consultancy kind of service you are providing in there.
No, no, I am not providing consultancy kind of services. I am working in a company. I am engineering background holder, but for knowledge, information about the solar, I
Mhm.
want to upgrade the knowledge for myself. If we get any opportunity in future, then it will be beneficial to me. That's why I am completely.
Okay, great. Uh, yeah. Anyone else? So for those joined recently, the link. So we are just discussing about our backgrounds and simply from which discipline we come from. Like a few of you might be from the mechanical engineering discipline or electrical engineering discipline, or few of might be still in school or colleges, or few of you might be working somewhere. So you may please share about yourself. Shyam Patel recently joined. Abhishek S is there. Manjunatha is there. Hello, are you there? Any one of you?
Hello.
Hello.
Oh,
Good
I am.
evening, sir.
Yeah, good evening. We will go first with Shyam Patel, then Ankur Pal. Is it okay?
Okay.
uh,
Oh,
Yeah.
I am Kumar Dinesbhai Patel. I
Uh,
am from Gujarat. I am working as a lecturer in Government Polytechnic Dahod.
oh, great. Great to be hear you. Yes. Ankur Pal, may you please?
20 pass out, and now currently I'm doing a job, private job in Manikaran Analytics Limited. We used to do like forecasting and scheduling.
Okay. Yeah, that's a
Like
great.
I am in solar department, like solar ka forecasting and scheduling we used to do. So I
Mm-hmm.
basically do for like different states ka forecasting and scheduling we used to do
Okay, that is.
like different sites.
Mm-hmm.
High megawatt quantum.
Mm-hmm. Okay,
So
so
analyze. I am at senior analyst post now.
okay, great. So you are basically the focusing on the solar thermal side or the solar photovoltaics or both?
Actually, I want to learn about solar energy, everything, how we can start up. Uh, I was basically thinking to do a startup like after 2 3 years
Okay.
in solar field,
Okay.
like dealership or like installation of panels and all
Okay.
like
Okay.
that.
Yeah.
Basically, I want to enhance my skills because I've done BTech now. So
Mm-hmm.
I want to enhance my skill like master in that. Everything I should be knowing. If like my juniors are coming in my company, like in our department, so I should be the responsible. Like I can answer for every question if they ask.
Okay, great. Any student we are here, undergrad or postgrad student?
Yes, sir. Myself Purvika, and I'm studying in the third year, NI National Institute of Engineering, Mysore,
Oh, great.
Civil Departments.
Civil demand. Oh, so we have a great mix of candidates here. So okay, so let's go with today's session, and I'm going to present the PPT here with you guys. Okay, I hope the slide is visible on full screen mode. Yeah. So
Yes.
okay, great. Thank you. Okay. So, in the past few lectures, we had the basics about the solar radiations and the solar angle and the application. Um, so, in this lecture, we will focus on the solar photovoltaics. So, solar photovoltaics means we have a photovoltaic device that is absorbing light, particularly the sunlight, and converting it into the energy. We called it solar energy. Okay, so what is the term photovoltaics? So, uh, okay, so anyone of you wants to share what you understand with the term photovoltaics? Yeah, anyone of you, uh, if can define term the photovoltaics? Okay, so we will go with the presentation itself, and we will understand what the term photovoltaics is called and how it works. Okay, so generally, what is the photovoltaic or PV technology? It is just a solar radiation is falling over a material. And what happens when the solar radiation falls over a material? It separates the positive and negative charge carriers of a material. So suppose we all know we use silicon as a material, but that is a semiconductor. Before going into it, so we all know that the material or any material is composed of any element, and element is composed of atom, and then there are comes electrons that flows uh, into the on the orbitals of the atom, right? Electron is flowing on the orbit of the atom, and with the positioning of the electrons on the orbit of the atom, and how the number of the atoms, the number of the electrons on any basically at the outer shell of the atom will define on what are the number of the positive and negative charges on it. So positive charge we are saying about the electrons, and negative charge no, sorry, the negative charge means we are talking about the electrons there, and the positive charge means there is absence of electrons that completes the outer shell of the atom. So we will be talking here about two types of charges, positive and negative charges, obviously. And the negative charge means the electrons, the presence of the extra electrons on the uh, outer shell of the atom. And negative charge and the positive charge means there is uh, we do not have extra electrons at the outer shell, rather there is a absence of the required number of electrons that can complete the orbit of the shell. Okay, so yes, so like if we call a substance, there is we are very familiar with the substance like sodium chloride. It is composed of sodium and chlorine. So whenever we see its atomic structure and we distributes it, so like what we do, the sodium, we got a positive ions on it, Na plus, we write it Na plus, and chlorine, Cl negative. So chlorine, so because so it has an extra electron, so that's why we are writing it as Cl negative. So there is a negative charge, and sodium Na positive we are writing. So because we do not have sufficient electrons there that can complete the orbit of the that can complete the orbit. Okay, so likewise we are defining it as sodium Na positive and Cl negative. Cl negative means negative charge on the chlorine ion, and sodium Na positive means positive charge on a sodium ion. Okay, so what happens when a light falls into any material or any substance, the material will absorb the radiant light, and the electron and holes, or the positive and negative charge, will get separated. Okay, once it will get separated, then there are some phenomena of the that can support the photovoltaics will occur. So how it takes place? Okay, so solar radiation will fall on any absorbing material, as we can see in this picture, and it can separate the positive and negative charge carriers. Then there is an electric field. So electric field, we can provide it externally, or it may be inbuilt within the material. So if we provide an electric field externally, so we need to have some external energy inputs there for that. But in the case of the PV technology, or utilizing the solar radiation, solar energy, so we have inbuilt electric field in the material itself. So then the electrons and holes will pass through this electric field, and then the current will be generated. So how we get the electric field inbuilt inside the material? So there will be a junction or inhomogeneity in materials, so that will facilitate an electric fields, and that inhomogeneity or junction ultimately provides the required electromotive force that helps us in current generation through the passage of the these separated positive and negative charge carriers. There is a question, by what material is absorbing material made of? Okay, so generally we will discuss in the further slides also, but in generally, like we are using generally we say silicon solar cells. So Ankur Patel, the silicon is the absorbing material made of. Okay, so we are using such materials, and then we will further read the p-type materials and n-type materials. These are we can say, if in general language, these are amalgamation of the two materials, conjugation of the two materials that can enhance the conductivity. So a material can be generally we use here semiconductor materials, and further for enhancing the conductivity and for enhancing the efficiency of the solar energy harnessing, we made different materials using these semiconductor materials as a base. Okay, so we will discuss this point in detail in the further slides. So as of now, the semiconductor materials, and in general phenomena, the silicon we can see here. Okay, correct? Okay, so moving ahead. Okay, so for simplicity, just take a picture, like there is any material, solar light is falling on this material, and the charge carriers in this materials are getting separated. Obviously there will be only two charge carriers, positive and negative charge carriers. These will be get separated, and to generate current, these charge carriers has to pass through a electric field, and the electric field uh, will come from the junctions in this material, or we can say simply the inhomogeneity, means the material is not homogeneous in nature. Somewhere there is when the charge can pass, there is some voltage fluctuation or other things, so it facilitates the required electromotive force, and that ultimately helps in the current generation. So we come at the junction devices. What are the junction devices? And these junction devices we use to build the photovoltaic cells or the solar cells. So as Ankur, you asked what kind of material. So in general, silicon semiconductors we use. So okay, so before going to semiconductors, we should know what is the materials we call it semiconductor, and what can be the general properties of these materials. Okay, so if we know the property of the materials, then we can identify the right set of material to use as as a solar cell. Uh, Initially we talked from the silicon semiconductor. Now we are testing different kind of semiconductor materials, and the different these materials are the single crystal materials also made of a single element, and these are the multi-element material also. We are doing research on this, and but these multi-element materials are packed as a single crystal material. So we should know, we should have a good understanding about the what are the semiconductors first. So semiconductors are, so if you see a metal or any material, so these are basically divided in three parts: conductor, semiconductor, and insulator, based on the flow of electrons or the charge carriers. Okay, so if any one of you may comment on what are the conductors first we should know the what are the conductors and why we need, then we will be able to understand why we need semiconductor here in harnessing the solar energy. So Purvika, what you understand by with the terms conductor? Hello, are you there? Okay, we'll go with Ankur Patel. Ankur Pal.
Yes, sir.
Yeah, so we are discussing about the conductor, semiconductor, and the insulators. So what you understand by the conductors? What type of material we can call them as a conductor?
But in semiconductor, like that conduction, sir, aluminum, silver, copper.
Can you please repeat? Your voice is breaking.
Sir, in conductor we can consider like aluminum and silver, copper, which we
Hmm.
use in wiring also
Okay.
for electrical cables. Mein. And so in
Yes.
semiconductor, it will be like group 14 elements like carbon, silicon, whichever comes in group 14, like valence in valence band, like there are four electrons, like four valence electrons
Mm-hmm.
in last orbit. And in
Okay.
sir, insulator, it will be like glass or plastic, like in which the valence shell is filled, completely filled, but there is no free electrons in
Okay.
last orbit.
Yeah. So the free electrons cannot move within the insulators, and in the conductors, the free electrons can move easily. So that's is a one differentiation based on the movement of the electrons. Okay. So further we come. Okay. So when we see there in any material, there are two kinds of the stage. We can say one is a conduction band, another is the valence band. Valence band will be always be filled with the electrons. So if I say the material is a conductor, so it means the electrons can freely move from the valence band to the conduction band, and these two bands are too close in case of the conductor, then there is no obstacle, and there is no, we do not need any external efforts for the movement of these free electrons. Okay, so this obstacle in case of the materials is known as the forbidden energy gap. If you see in the case of the semiconductor, so there is a bottom, so there is a bottom red box. This is our valence band, and electrons are filled in this band, but the conduction band is little far away from this valence band. So the gap between these two is called forbidden energy gap, or we generally call this at forbidden energy band also. Okay, so but in this case the gap is moderate. If we provide a little external effort, the electrons can move from the valence band to the conduction band. But if we see in case of insulator, so in case of insulator, the forbidden energy gap or forbidden energy band is quite higher than the semiconductors. So in this case, we need a very high external force to flow the electrons from valence band to conduction band. So, but this uh, band gap is quite higher, even uh, even than the frequency of the photons we can apply on the materials. Okay, so based on the forbidden energy gap, we can differentiate these three kind of materials: conductor, semiconductor, and insulator. Insulator will be having a higher forbidden energy gap, and then we come to the semiconductor. It will be having a moderate energy, moderate forbidden energy gap, and conductor, it will be having no forbidden energy gap. So Eg will equal to 0 in this case. Okay, so in the case of semiconductors, if we apply a sufficient energy there, because the Eg is quite less than what the photons we can apply on the materials. So in the presence of the sufficient energy, the electrons from the free electrons from the valence band will pass to the conduction band, and then they can move freely. So that's why we use a semiconductor, because in this kind of material, if we apply a solar radiations, so these will facilitate flow of electrons that further can be used for the energy generation. Okay, so if you talk about the semiconductor, there is two terms: intrinsic semiconductor and extrinsic semiconductors. So like we discussed in earlier, there are pure materials like silicon. These are single element materials. So these pure materials will be known as intrinsic semiconductor. So intrinsic semiconductors will be having a Fermi level in the middle of the conduction and valence band. Okay, so we will come to the Fermi level. Let's understand with the density of the charge carriers there. So density of the free electrons in the conduction band will be equal to the density of free holes in the valence band. So holes are nothing, it is the just absence of the electrons. Okay, so in this case of intrinsic semiconductor, so the density of the free electrons in the conduction band and density of free holes in the valence band both are equal, and this can be used for the solar energy harnessing. Then we come to the extrinsic semiconductor. What happens in the extrinsic semiconductors, and why we need these kind of semiconductors? So in any case, we need to enhance the conductivity of our material, especially of intrinsic semiconductor. We dope these semiconductors with an external materials with an another element, and we call it as impurity ions. So the statement is written that extrinsic semiconductor are doped semiconductor. Doped means we are doing a doping of another external element over the intrinsic semiconductor, so like over the silicon. Okay, so that's why these are called doped semiconductors, and we are doing a doping with controlled quantities of the specific impurity ions to get extrinsic semiconductor. And based on what kind of material we are using for the doping, we will be able to manufacture p-type materials and n-type materials. Okay, so what are the p-type materials and n-type materials? So if we say like, okay, so there are semiconductors, like we see a silicon, a semiconductor is there. It is having 4 electrons in its outer shell. Okay, and we are having another external element. Generally, okay, if we talk about the p-type material here, and n-type material. To manufacture a n-type material, we use a pentavalent. N-type means there will be more extra negative charge available after doping, and p-type material there will be extra holes available after doping. So if you use a group 5 materials from the element, if you see group 5 on the element periodic table, so if you use the group 5 material, we will be able to manufacture n-type materials. And if we will be use the group 3 materials like boron, so we will be using to get a p-type materials. In the p-type material, we will be having the extra holes now, and in the n-type material, we will be having extra electrons. So if I see the silicon, it is having the 4 electrons in its outer shell, and then we are taking an external element P. That is the phosphorus. We have taken it from the group 5 table, and this is having a 5 electrons on its outer orbit. So 4 electrons will able to freely make a covalent bond. This one. So the 4 of the electrons will be able to make a covalent bond with our intrinsic semiconductor, with our pure semiconductor, is that silicon. Yes. Okay. So, but after making a covalent bond with 4 of the electrons, then there an extra electron is left over there. So this is not a free electron here. So this free electron makes the material a n-type material. Okay. So basically, what we need to make a p-type material or n-type material, the valency of this element will be high, should be higher or greater than our intrinsic pure semiconductor. Okay. Now comes what is the valency. Valency is simply the number of the external atoms available there to make bond with another atom. Okay, so this way here the valency is the 5 for the phosphorus, and the 1 we have a free electron there. So this free electron gives property to manufacture a n-type material. Okay, there is some. Okay. So like we talk about the n-type material. Again, like there is another material we are using here, lead. So this is sharing this is having 5 electrons on its orbit, means on its outermost orbit. So 4 of the electrons will make a covalent bond with silicon, with the 4 atoms of the silicon, and then we will having the 1 extra free electron that will contribute to a n-type semiconductor. And then we see a if you want to manufacture a p-type material, so what will be happening? We will be taking a group 3 element here. So like boron we have taken. So boron, there are only 3 electrons freely available on its outermost shell. So one of them will make a covalent bond with this silicon, another will make with this silicon element, another and the third one will make a covalent bond with the silicon element. But now this silicon element is left free. So this way we create an extra hole here. So due to the presence of extra hole in this set of the materials, the doped materials, so we will be able to get a p-type material. So these are called as extrinsic semiconductors. So remember, for a n-type material, we need elements, we need doping with elements of group 5 group 5, and for a p type material we need elements from group 3. So in the questions it may be asked either just a group, the name of the group might be given there. So like a group 5 element, the doping with group 5 element, or the doping with the group 3 element, then we need to solve the question. Or otherwise simply the name of the doped element might be given there. So if it is given that there is a group 5 element, so okay, so we are going to make a n type material, and if there is a group 3 element, we are going to make a p type material. Okay, so now how it works, like there is a, we make a p type material using a boron. So boron will be requiring, there is an extra hole now available in this doped material. So if there is an extra hole, it wants to complete the outermost orbit, it wants to fill its valency, so it wants an extra electron in its valence shell. So in this case, the conductivity will be held in this valence band. And if we say there is a n-type material, n-type material means there is an extra electron, so the material wants to lose its extra electron, so this way the conductivity will be held in the conduction band. So this way the p-type and n-type material works. But this p-type and n-type materials we cannot use individually for harnessing the solar cell. So we need to merge these two materials, p-type and n-type materials, to make a single crystal. And there is one more point, these two materials, p-type and n-type, were created for the purpose of the merging itself. But what will happen when we will merge these two kind of materials? Now this n-type material, because of this free electron, wants to lose this free electron, and this p-type material, because of this hole, wants to gain a free electron. So if we make a single crystal of these two materials, so we will be able to move freely the electrons from one type of the material to the another type of materials. Okay, so we will discuss further on the concept of the conjunction of the p-type and n-type materials, and we will be making the p-n junctions there then. Okay, so before that I discussed earlier, in the intrinsic material, these are the pure semiconductors having Fermi level in the middle of the conduction and valence band. So the basic theory is the density of free electrons in the conduction band and density of free holes in the valence band. Remember, the free electrons only will move from the valence band to the conduction band. So that's why we will always see the density of the free electrons in the conduction band. Vice versa, we will see the density of free holes in the valence band. So the density of free electrons in the conduction band and density of free holes in the valence band will be equal. So why? Because the Fermi level is in the middle of the conduction and the valence band. So now we understand first what is the Fermi level. Okay, so the Fermi level is nothing but it is an apparent energy level within the forbidden energy gap. So forbidden energy gap we discussed, the gap between the conduction and the valence band, and it is just a Fermi level, just it is a apparent energy level which majority carriers electrons in n-type materials and holes in p-type materials. That's the basic theorem. And so this all defines that electrons and holes both are excited to become the charge carriers. So then if there is Fermi level exists there because of the forbidden band gap, and the electrons want to excite to become a charge carriers. So both the carriers, means not only the electrons but the holes also are wants to excite to become a charge carriers. Then what is the probability of the majority charge excitation? So the probability is defined as the exponential of the means E psi, where the E is the charge of the electron and hole, and psi is the electrical potential difference between the Fermi level. Between this Fermi level, I will highlight it with green. Between this Fermi level and the valence, or so Fermi level is somewhere at between. So psi will be the electrical potential difference between this Fermi level and the conduction band, or between the Fermi level and the valence band. And so always when we will be talking about the Fermi level, and we are talking about the probability of excitation of electrons or holes, so the probability will be calculated with reference to the Fermi level itself. So that's why we are calculating the potential difference between the Fermi level and conduction band, or the potential difference between the Fermi level and valence band. Then we come to the temperature. We always need it in Kelvin and Boltzmann constant. Okay, so next, if so, this is the general probability of the major carrier excitation. So if we are having the n-type material or the p-type material, in both the cases we need to know what is the Fermi level. So Fermi level is basically calculated based on the energy acquired within the material. So if we are talking about the n-type material, so we are focusing on the conduction band. If we are talking about the p-type material, then we are talking about the valence band, because so we will seeing with reference to where the electrons and where the holes are situated in a particular type of the material. Okay, so for this for n-type material, okay, for the n-type materials, we will be having the formula like we will be calculating based on the EC, conduction band energy, and plus KT, K we know the Boltzmann constant, T is temperature, natural log of the donor concentration available upon effective density of states in the conduction band. Means what is the effective density of these in the electrons in the conduction band. And then we will be talking about the p-type materials. Here we will be seeing the valence band energy and acceptor ion concentration, because p-type material is always be having the acceptor ion. There is a one hole is extra hole is available there, so that can so in the p-type material there is an extra hole available that can accept the ions. So we will be checking out the what is the acceptor ions concentration, and then what is the density of states in the valence band. So like, okay, so we will take this example to understand how we use these terms EF, EC, KT, natural log of ND and NC, and these different terms. Okay, so the calculation is the question is the Fermi, calculate the shift in Fermi energy level in a silicon crystal doped with a V group impurity of concentration. The concentration is given 10 to the raised to power 15 centimeter cube. Effective density of states is given, and the band gap is given. The temperature is given. Okay, so we need to calculate the shift in Fermi energy level. So for that, first we need to calculate the Fermi energy level. Okay, so for the calculation, okay, okay, so coming back to you that like there is given a silicon semiconductor we are having, and it is being doped with a V group material. So what kind of material we are going to manufacture now? The first we need to identify this thing. Any one of you can please? If we will dope silicon semiconductor or pure intrinsic material with a V group element, so what type of material we are going to manufacture? You can write on the chat box also, or you can just unmute yourself also. Anyone of you can please? Okay, so still if you are getting confusion, like simple, we are having a semiconductor, and if we are having a group 5, if we are doping it with a group 5 element, we will be getting an extra free electron there, and by this way we are manufacturing n-type materials. And if we are doping pure semiconductor with element of group 3, then we are getting an extra hole there, and with this way we are going to manufacture a p-type material. Okay, clear? So first, because we are having two formulas here, there is a different formula for n-type material and different formula for p-type material. So what type of formula we have to choose? So we should have clarity that what kind of material we are going to manufacture. So if we are taking a group 5 element, then we are going to manufacture a n-type material. And if we are going to take a group 3 element, we are going to manufacture a p-type material. Okay, clear? So now we are clear about what formula we have to use. So we have to use that formula for the n-type material. EF is equal to EC plus KT natural log of ND upon NC. So EF, Fermi energy level, we need to calculate. So basically the shift in Fermi energy level is asked. So first we will calculate the Fermi energy level, then we will be able to comment on the shift in Fermi energy level. So for the n-type material, we will be focusing on the conduction band energy EC plus K is the Boltzmann constant and T is the temperature, natural log ND upon NC. Okay. Okay, so now two things are clear to us. One is that we are going to manufacture an n-type material, and the formula, yes, Ankur, it is correct that n-type material while doping with group 5. Okay, so we are going to manufacture an n-type material, and okay, so formula is clear. So anyone of you is if solving this question on paper, I hope you guys might have pen and paper with you, correct? So if anyone is trying to solve this question on the paper, please let me know. I just wanted you guys to uh, take the values given, whatever is given in the question, note it down and try to fit these values in the formula. If anyone of doing so, please let me know. Just should I wait or I should move toward the solution?
Sir, the screen is not changed, I think so. Slides are not changing.
Okay. I will share the slide and I will wait for a couple of minutes. Okay, is it the slide is visible now? Hello, Purvika?
Yes, yes,
Yeah,
sir.
yeah, slide is visible. You may note down the formula, then I will go to the question again. If you will note down the formula, please let me know. So we can wait for 1 minute for this. 1951 it is here. So formula is EF is equal to, EF is the Fermi energy level, is equal to EC. EC is the conduction band energy, plus KT. K is the Boltzmann constant and T is the temperature. Note down the temperature. T is in Kelvin. So in question it is given in the degree centigrade. So to convert it into the Kelvin, we have to add 273 into the degree centigrade. So then we will get the temperature into Kelvin plus natural log of Nd plus Nc. The donor concentration and effective density both are given in the problem. So going back to the problem. Okay. So yeah. So anyone of you who is putting the given values on the formula may let me know what are the values given for what kind of things, like what is the value of the EC given here, what is the value of the temperature given here. Okay, have you noted down the question?
Yes, sir.
Okay. Okay. So okay, if any one of you have a little clarity about the terms given in the question, you may please let me know. Okay. Okay, I'm again showing the question. Meanwhile, if anyone have noted down the question, just uh, whatever you are thinking about the given values, let me know, and then we will go ahead. I'm showing the slide again. Okay, is the slide visible now? Okay, so we will start from the one by one, starting from the EC. EF we have to calculate, Fermi energy level, and uh, EC we have to calculate. So EC is given here 1.1 electron volt. Okay, after EC we know the K, the value of K we know.
Sir, slide is not changed, sir.
Okay,
We are not able to see the question.
okay, is it visible now, slide?
No, sir, it's still in the old slide.
Wait a second. Okay, is it visible now?
No, sir.
Okay, so is it the same for everyone? If anyone is able to see the slide clearly, let me know.
Yes. Yes.
The slide is
Slide
visible.
is visible.
Okay.
Yes. Yes. Yes.
Okay, so I am repeating the terms given here. The band gap 1.1 electron volt, Purvika. It is EC. The value of EC is given here 1.1 electron volt. Then we come to the next term. The value of K we need. The value of K will be, it is the Boltzmann constant, and the value of K will be 1.38 into 10 raised to power minus 23 joule per Kelvin. Okay, so whenever we are solving the question, make sure the units are the means at the same standard for each of the values. Okay, so the temperature and then Boltzmann constant, and then we come to the value of Nd. The value of Nd is also given here, and it is 10 raised to power 15 centimeter cube. The concentration of the impurity and the effective density Nc is given here 2.82 into 10 raised to power minus 19 centimeter cube. Okay, so basically there are two methods to solve the questions and to check out the units for that. Like if I say the Nd by Nc, so Nd by Nc is always going because it is in dividend, so centimeter cube will cut with the another centimeter cube of Nc. So the now we will be having EF is equal to 1.1 electron volt into K, Boltzmann constant into temperature T. T will be 27 plus 273 into natural log of Nd upon Nc. Okay, so if you see here, so the value of EC we will use 1.1 electron volt, and K we will use 1.38 into 10 raised to power minus 23, and then we are calculating the Fermi energy level on the charge basis, per charge basis. So 1 electron holds overall 1.6 into 10 raised to power minus 19 units of charge. So if you are talking about the per unit of charge basis, so we have to divide by this value into 300 is came here from 273 plus 27 degree centigrade. So the temperature is 300 Kelvin, natural log of 10 raised to power 15 Nd upon Nc, the density 2.82 into 10 raised to power minus 19. So we will be able to calculate the Fermi energy level now, 3.1 electron volt. So then now how to calculate the shift in the energy level? Okay, to calculate the shift in the energy level, we have to subtract the value of the basic energy level, that is given 0.55 electron volt. So the shift in energy level now will be the 2.55 electron volt. So what happened? The total Fermi energy level is 3.1 electron volt, and now it got reduced by 2.55 electron volt. Now if we dope the material with it shows that if you dope a material with external element, it will reduce the field. So by this way it will help us in increasing the conductivity. Okay, so now we comes toward the P and N junctions. Okay, so we will quickly complete this topic, P and N junction and its characteristics. We will go to the another numerical. Okay, P and N junction means I said that we have to make a single crystal of these two elements, P type material and N type materials, so that we can use this single crystal for the flow of electron and holes. Okay, so what happens when electron and holes, there are free electrons and there are free holes available, one in the free electrons in the N type material and free holes in the P type materials. These free holes and free electrons move toward each other, and at this junction point here, or in detail we can say here at the junction point, the free electrons and free holes will merge into each other. This is called a recombination, and because of this recombination we get a depletion region at the junction. Okay, so what happens, like this is in N type region, there are some positive donor ions, as we say in the word when we make a N type materials, and there are some negative donor ions in the P type materials, but the N type material had a free electrons and P type material had a free charge. These move toward each other and created a depletion region. So what happens when this case is when we just manufacture a material in the factory. So that time the material will be in this state simply. Now what happens when the solar radiation falls on over these materials? So before going to that concept, we know there are at the junction there are forward bias and a reverse bias. Forward bias and reverse bias means if we are adding an external battery with our newly manufactured PN and single crystal. So if battery is added, like the negative point of the battery is connected with the n-type material and the positive point of the battery is connected to the p-type material. So in this case, the electrons from the battery will flow toward the n-type materials. And if the electrons will flow toward the n-type material, what will happen? Already few electrons are flowing from this n-type material toward the junction. Now more free electrons will flow toward this side. And the second thing, the holes will flow toward the junction side. So in this case, what will happen? If in the absence of battery, this is the depletion region where electrons and holes are getting merged, the recombination phenomena is taking place. And if you are providing external electrons from the outer side, now with the more number of the electrons, the thickness of this region will increase. And if we say that reverse bias, when we connect a positive terminal with the positive side and a negative terminal with negative side, so what will happen? Okay, so the free electrons will move from this to this side and holes in the reverse direction. So this way will not work. So when we see, okay, so I will directly come first to the photovoltaic effect. Then what happens when solar radiation falls over a surface? So like we are trying to move the electrons or the holes with the external electric field or the external source of the voltage like battery there. So we can move these electrons and holes in the presence of the light also. So what will happen? In the presence of the light, the photocurrent will generate, and the direction of the photocurrent will always be opposite to the what we saw just in the forward case. So by this way, if you see the p and n junction characteristics, when there will be no external bias, like we are not applying any voltage, we are not having any battery set there. So in this case, the reverse recombination current in an isolated junction will be equal to the current generated through passage of carrier charges. So there is no movement. So there is a balancing of the current generation and the recombination. So what will happen if we have a forward bias of voltage V? We are having an extra battery here, and the n terminal is connected to the n side. So in this case, we will having the reverse recombination current as Ig is equal to exponential of EV upon KT minus 1. So but in the dark case, when there will be, we have to calculate the total current. The total current will always be IR minus Ig. And similarly, in the case of the reverse bias, so then we will having a saturation current under the reverse bias case, and that will equal to the Ig. So we can calculate with this formula, and I will share this PPT over the Google Drive also, so you can get all these formulas from there. Okay, so if you talk about the IO, the saturation current under reverse bias. So first, if you have to calculate the total current in case of the no illumination, we have to calculate first the value of the IO. So all others value we know, the what is the value of the EVA, what is the value of K and T, and so we need to calculate the IO. For this there is another formula. We calculate it based on the energy gap. So and we use a non-ideally factor A, a constant value there, and based on this we will be able to calculate the IO. Further, we come to the photovoltaic effect. Photovoltaic effect, we have read that solar radiation is falling over the surface and the current is flowing, but the direction is opposite to the forward dark current case. So in this case, generally we use the term IL for the photocurrent, but if there is no external applied voltage, no battery we are using, the photocurrent will be measured as the short circuit current, ISC. So we will be calling as IL or ISC. So there are two formulas different there to calculate the overall cell current. So whenever we will be calculating the overall cell current, so we will be checking first if there is an external applied voltage, if there is any battery. So for this the formula will be this, and for another case when we are saying this there is no external applied voltage, so formula will be slightly different. Okay, so okay, so I won't go through in depth in this in this part. So basically whenever we are checking the photovoltaic effect, we have to check the maximum power we can generate, and we have to check the maximum load current. So in this case we always study with respect to the with respect to the open circuit, means there is no overall current, and the voltage will be whatever the voltage is with respect to the open circuit. So on this basis, with reference to the open circuit basis, we will be able to calculate the value of the maximum load current and the maximum power current. So like there is another example, so which asks to calculate the maximum power output per unit of cell area. Okay, so for the for its calculation we again need what is the current value at the saturation case, what is the short circuit current value, and based on this we will be calculating the reverse saturation current density. And once the value of the AC, in the case of short circuit current, the value is 250 ampere per meter square is given. So we are using this formula, and then we will be able to calculate the maximum power output per unit of the cell area. Okay, question. Okay, so okay, as we have already run out of time, so I will be sharing this PPT in the Google Drive folder also. I hope it is accessible to you. Is it so? The Google Drive folder from NPTEL site is accessible to all of you? Okay. Okay, so the PPT, the slide will be available there. Hello, Harsha. Are you speaking, or is there some background noise?
Oh, sorry, I'm sorry.
Okay, okay. Okay, so the PPTs are available there, so you can go in detail with through this formula, and then you will be able to solve a few of the more problems. Okay, so let's meet in the next session on the next Tuesday. Okay, thank you very much, guys.
Thank you, Mohit.